Hello everyone, I will be talking about the electricity consumption of network-connected devices in the residential sector in Germany, a study in collaboration with the Fraunhofer Institute for Systems and Innovations Research in Karlsruhe. I'll start the presentation with some introduction, the research questions, the methodology, results and discussions, and finally the limitation and future work. So the study is motivated by the information provided by the International Energy Agency for Germany, the year 2018, where the residential electricity consumption amounted to 25% of the overall final consumption by sector. And so although this figure shows stagnant consumption, the rapid transformation of digitalization has increased the use of network-connected devices and thus also increased data traffic between devices. And a reported figure from another report suggests an exponential increase in the global transfer of data with this rise in internet traffic. So to have a general overview, network-connected devices are sometimes referred to as Internet of Things and smart devices, and they reflect the ability of a device to communicate between one another. And so its communication results in increasing amounts of data that must be generated and processed. And that's where data centers are built. It's to meet up this demand because these processes require power and data storage capacity. So the question is, what is the upstream energy related to network-connected devices in the residential sector? And so in this study, upstream energy refers to the combined energy that data centers and wide area network involved in the transfer of data between connected devices consume. And so the second question is how much of electricity consumption in the residential sector is contributed by the connection of smart devices. In these, the following study uses a scenario analysis, and it's simulated to query the effects of electricity consumption through the change in policy, user behavior, and developments of the improvement of data center efficiency. A simulation model used in this study follows a bottom-up approach and is extended from the existing forecast residential model by Fraunhofer eceee, which is used to support strategic policy decisions. So it is a techno-economic model which is able to analyze the technical and economic performance of a process and allows for comparative analysis. What this also means is that the model is also able to have an extensive technological detail by having different sectoral levels. And this is the structure of the forecast residential model with three different sectoral levels of end-use technology and efficiency classes. So the extension is that smart devices are either introduced on the technology level or they're introduced as an entirely new end-use. The simulation period for the study is between 2015 and 2035, and it uses a vast growth model to determine stock transformation, where it considers the path between new technology, entering the market, and replacement of the old technology, and it's therefore influenced by innovation, limitation, and the market potential the VAST model tells us exactly how much stock of appliance should be in a particular year, but to determine end user purchase and market share of an end use, the utility function and market share functions are computed. So the utility function simulates customer purchases based on cost, and here based on the net present value, applied subsidies, average maintenance and operation cost, and is then divided by the number of viable alternatives. The market share uses a logic approach because in reality purchases are not only based on monetary value, but can be very much influenced by personal preferences. And these preferences are represented by the heterogeneity of the market. And to have a better overview of this, for example, we have an expensive television and a cheap television, and we know that not everyone is going to purchase the cheaper version because that's just not how the market works. And therefore, this lambda catches exactly this influence of choice by customers. The methodology to calculate upstream energy is presented here. So the upstream energy is the data flow between data centers and residential data demand, but the boundary of the network process includes the on-site networking equipment, such as the set-top boxes, wireless router, and the access networks such as a DSL or fiber networks. And in this study, only DSL connection is used due to its dominance in Germany. So the calculation follows a data flow which contributes to the demand in electricity. And from this equation here, we can separate the different connections. First, between the user devices to the on-site networking equipment, which tells us how much data is demanded. And this is given in gigabytes. And second is the energy intensity of the access network, which measures the efficiency of data transmission through the internet. And this is given in kilowatt hours per gigabyte. And third is the data center efficiency or power usage effectiveness, which provides us the information as to how effective the data center operates in respect to the power it requires to maintain its IT equipment. And then this study is given as a global parameter. So I would like to have a little focus on the energy intensity because it's based on a study by Aslan and measures the efficiency of internet data transmission. Because it will be a huge topic of discussion. So the background of energy intensity is first the definition, of course, it's the measure of efficiency of data transmission through internet over time. And according to Aslan et al., it is decreased by half every 2 years in developed countries. So the initial study produced estimate between 2000 and 2015, and in this study, the remaining years were extrapolated. And this graph on the left is how it would look like after being extrapolated. So the methodology for the electricity consumption is first to determine the different modes of operation. And these are the different modes of operation addressed in this study, which is the operation on mode, standby mode, and then network active network standby mode. An easier method to identify these, how this is used, is to look into an example. And again, we have the television, we have a conventional, and we have a smart television. And so these two have a similar primary function in which they display content through broadcaster channels. But what they have in different is the secondary function where conventional TV does not have. And a smart television has a secondary function where it's connected to the internet to display online media. And so in this case, the electricity consumption in a conventional television is divided only between operation and standby mode, whereas a smart television has all the 4 different modes. And this concept applies to all venues where the primary and secondary function is distinguished first in order to answer the research question. To determine the influence of policy, user behavior, and efficient data centers and electricity consumption, scenario analysis was computed. And with every scenario analysis, we start first with the reference case, which is in this study called as business as usual, and it considers all minimum policy requirements. And then we have a scenario where the best available technology is selected, and this means that only highly efficient devices enter the market. To address user behavior, smart device purchases were investigated. The target share of 50% or more smart device purchases were set to meet by 2035. And another scenario addressing user behavior is through the increase in data transmission, where a 30% additional year-on-year increase in comparison to the business as usual was simulated. The data to investigate the data center efficiency, the power usage effectiveness of 1.12 by 2035 is set in this scenario. And the reason why 1.12 is set is because of the lowest recorded power usage effectiveness in 2018 by Google. But in the context, the data center efficiency for the business as usual reaches 1.4 by the year 2035. Moving on to the results and discussion, all the answers are based on scenario analysis. So to answer the first research question, we first look into the electricity demand without the upstream energy. And immediately here in this figure, we see that the biggest reduction is from the best available technology, followed by increased smart device purchase scenarios. And this is because smart devices are commonly more efficient themselves. The remaining two scenarios have no effect on the electricity consumption, and therefore we look into the combined residential electricity and upstream energy demand against the business as usual scenario. We see some change in the data transmission scenario, but the data center scenario remains unchanged. And remember, according to the equation used in the study, the trend in upstream energy is dependent on volume of data transmission, energy intensity of access network, and the development of data center power usage effectiveness. But we see little to no difference in increasing the efficiency of data centers, and this raises an important discussion on the energy intensity of access networks with respect to the direct connection between data demand and energy consumption of data centers. And here is a summary of the results with the two decreasing demand by the businesses best available technology and the increased purchase of smart devices and the increase in demand in terms of data transmission in the upstream, in the combined residential and upstream energy demand, and no difference in the data center scenario. And looking deeper into upstream energy in the reference case, the study finds that there's a year-on-year decrease in upstream energy, although there's a year-on-year increase in data usage. And this is again due to the energy intensity value taken for the study. So we know that the upstream energy has a high influence from energy intensity. And but when we look a little closer into the figure 8 on the right here, we also notice that smartphones have a high share in data usage, and maybe it pops a little question, but it's a study by Ericsson expects this trend to actually grow due to video-rich applications and the adoption of immersive consumer services such as virtual reality and augmented reality. But due to the simplicity of the model, I cannot conclude here, but there is a limitation that needs to be addressed. And so before we move on to the final slide, look into the network connected energy demand to answer the second research question. And here we have all the different operation modes aside from the operating mode. And we can see that the electricity demand in red, which is represented by the network standby, is consistently higher than the normal standby mode. And this is actually reflective of the high amount of wide appliances with network standby mode. And finally, the study is only strengthened by addressing the limitations and its possible future work. So the model is limited by the simplicity of assuming only DSL connection throughout Germany, and fiber networks are slowly being rolled out. And this introduction to the model, the distinction actually allows to investigate what potential other access network may provide in terms of energy intensity. And of course, the limitation of the model is the simplicity of energy intensity, where considering a direct translation of data to demand, it cannot be easily translated with just one unit. And so the future work should consider the complexity of energy intensity and needs to incorporate the different types of access network, the usage hours of a device being connected, the data transmission based on sources, and the distance between source of demand to its nearest data center. And this is where the power usage effectiveness of a data center is important instead of just a global parameter. And then what would be also additionally interesting is the addition of demand side management to further illustrate the electricity abatement caused by smart devices. And that is the end of my presentation, and thank you for listening.